an example of why, okay? And there are a few others that I can show you examples of, okay? Right, so what's the system? Remember, I was showing you yesterday about the process that the Spark tools or the Praxis company uses, where they go from requirements to a formal specification to a formal design and the actual Spark implementation, which you will be doing yourselves soon from next week on into the end, okay? So we're going to be learning about how to do Spark programs, and we're going to have a glimpse at the various assurance processes that go around in this. Okay? So in the example that I was talking about, Tokenea, that I mentioned, it is the system by the NSA. Let me show you. You can actually download this and look at it yourselves. The files or the source code for Tokenea. What is it now here? So Tokenea, what is it there? So the whole code is there, all the documents and so on. But what's interesting about this, so you get the first document, we already opened it here. The first document is the so-called protection profile, and the protection profile is a requirements document, a bunch of English explaining what the security agency wanted out of the system. Okay? So if you like, it's your wish list. Okay? All the stakeholders, the owners of the problem, sat down and actually contracted somebody to describe what the Tokenea ID station wanted, and this was Spree, a company that the NSA hired. So in this document, what I wanted to show you are things like, let's see, yeah. So audit data generation, they have a number, and this is common in the requirements, right? So you get numbers in a naming convention that you attach certain descriptions in English to. So let's read one. Let me pick one here. Yeah, so for instance, the ID station shall record in the unique audit record at least the following information: the date, the time of the event, what kind of event happened, who was the subject that went there. Is it a guard? Is it an officer? Is it a administrator? Is it a user? What's the outcome? Was it granted that access, or has it failed? And if so, why? And then get an audit trail of what happened. Okay? So that's what the security people wanted whoever is going to design the system, us, to deliver. Okay? With a level of assurance that was EAL5 and beyond within time and budget. Then the question is, how do you deliver this, and what kind of tools and techniques do you use? So that description there goes on and on from various different requirements, and if we go to this picture, it's pretty much what's in there: security target and the requirement specifications. Okay. From that, they then will derive both the formal specification and the code. I will skip this bit just for the sake of time, but they also derive tests and other things. I'm just trying to give you a concrete example, as real as it gets, of the use of what you're going to learn here. Okay. So if you look at what the formal specification looks like, that's another document called 42.1. I am in page 19. So this document is, again, a formal specification of the Tokenea ID station. It is signed by the NSA again, and if you go to page 19 where I was, it has some data about, never mind what the language is like. This is VZ in particular, but for those who know VDM, they're very similar. The point there is you define some types, some mathematical types, you define some relationships between these mathematical types, you define various conditions for them to be true, and again, the mathematics there doesn't really matter, but the point of the exercise is to say, if you want to know what to log, for instance, you look at a set of auditable things, and then you decide among when they are to be logged, whether or not they are new or old, and that determines what you're going to do with the audit log. In other words, do you trim the audit, do you trim the log, or do you update the log? Now all these get associated with them, let's see if I find it, a bunch of numbers here. Okay? So that means each piece of mathematics above is being realized by, is realizing each one of the English requirements written down there. You see the link? So somebody writes an English sentence to explain what FDP ACF 1.4 means, and then somebody else comes here and says, all right, that is realized by this particular description in mathematical notation, which basically means if there's somebody there and that somebody's a guard, then the only thing it can do is override the block. There is somebody there, that's an implication, by the way, so you can think about what we're learning here in terms of the logic. Think of the, remember I said that you would have simple set theory or equality or the basic logic connectives, okay? If you take this to be A implies B, okay? Here this is basically A implies B and not A and C implies D and so on, okay? But I hope this gives you a glimpse at what this is trying to achieve. It's saying, well, if nobody's there, there is nothing you can do. If somebody is there and then somebody's a guard, then you can override the lock and basically enter the room. If it's an audit manager, it can look at the archive log. If it is a security officer, it can change the configuration data or shut down the system altogether. And again, from this description, say, of how the data is to be constructed, it goes down all the way to actual, this is Spark code for the ID station. In this case, it's for the configuration data of the ID station, whereby you get types just like you do in other languages. If you see in VDM, this looks like a typing variant for a subtype. But more interestingly, you get to see also, let's see if I find the one here. You obviously are not going to write anything complicated like this, but remember that raw duration example that I was showing you in the slide? That it is, the division by 10 rather than the multiplication by 10. That particular error over there was explained there why the analysis failed and under what conditions. And then if you want to know what the analysis is, and that's what you're going to be doing, okay, you can read more on this about token here. So I hope with this you get a kind of a glimpse at the process that goes on from what you want written in English all the way down to what you want written in a program that's accountable and has a proof to demonstrate why what you claim to be true being true. Okay? Right, okay. So to give again another glimpse at an example of this, I actually found, I mentioned yesterday about the verification conditions that Spark generates, and we've been talking about square root as well as an example. So if you write, I played around with this a little bit, if you write a Spark program for square root, it looks like this. I mean, this is not the Spark IDE you're going to use. You're going to use Ginat by Adacore. So I'm basically using Spark within Isabelle just because I like to do that. But basically, you get a function with a signature that's giving you the integer square root of 2 naturals. So it's an approximation. So in a way, that implementation does not take error into account, but just gives you a approximation under naturals. The interesting thing about this is the post condition there that says, well, r times r is less than or equal to n, and so if r is the result, that means, so say take n to be 4, the result's going to be, whatever the result is, it needs to be less than or equal to 4, but then it's, if you sum 1 to the result, its product is certainly greater than 4. So that's kind of embedding your error fixed in the post condition. You're saying how much the error is. Yeah? An actual implementation of this in Spark looks like this, where again it's similar to what we were doing before. where you get the Gaussian guess in the loop condition to exit. And you don't need to worry about this program or anything. I was just trying to show it as an example. As you run the Spark tools on this, okay, I mean, this is just a loop that similar to the one I wrote earlier. When you run the Spark tools on this, you get the following output. It tells you some declarations, things that it takes for granted. Basically, your libraries of how to handle arithmetic in terms of, you know, what's the max int, min int, if you know Java. It also tells you certain rewrite rules, namely theorems that it has in its armory of knowledge already proved about arithmetic. Okay, and then it then says, okay, here is a set of proof obligations. So as you press compile in Spark, you get this as a report rather than a compiled file. And in it, it gets various proof obligations that are true automatically, namely the tools are good enough to discharge the proof obligations. And then there is one that it cannot discharge, and it has to do with overflow of the result. And if you think of it, natural numbers in Spark go up to a maximum. Okay, in this case, a 64-bit number. Okay, so if your n is going to be too big, then r plus 1 times r plus 1 may go beyond the overflow, and that's what this proof obligation is saying. Okay? So the way to read this is you have a bunch of hypotheses in conjunction, and that's implying your conclusion. So this is basically age 1 and age 2 and age 3, blah, 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 implies C1 and C2, and that's your proof to do. Okay? Now, this particular one, the Spark tools cannot discharge. And then you can use other tools like Isabelle to do that. And again, we're not going to go anywhere near any of this. But I thought to show you, so that, remember, keep it in mind when we're doing our proofs by hand, where is this used for real, as it were, okay? Because a lot of the exercise in this module is to, one, expose you to these technologies and techniques, as well as giving you a handle at how to write Spark programs, okay? And understand the technology behind it, rather than be skilled experts in theorem proving, okay? But the proof obligation that it cannot discharge, that is your goal, right? 2 times r is less than or equal to this big number, 2 times r is less than or equal to then this big number. And whatever you do to discharge this proof, you play around with arithmetic enough, and eventually you can show that indeed by simplification this is done and all verification conditions have been proved. And Spark End basically says, is there any more to be proved? And if there are, then this fails and you're not done yet. Okay? The point there is, this kind of so-called proof script is readable enough in the sense that you're saying, okay, if you assume that r is a natural number, then either it's 0, 1, or 2, or it's less than or equal to 2. Sorry, strictly less than 2, and you can prove that, and then if you know about proof, this is a readable script. You don't need to understand the theorem prover to follow that proof. You just need to know how proof works. Anyhow, these proof obligations are generated by the Spark examiner, and then you get to discharge them as you go along. And once you finish them all, then you can claim that your software is up to a particular standard. Okay? Right. Let's go back to our slides themselves. So it's interesting also to mention something else about the Spark process. The tools, not just the tools, the company provides a warranty that's unique. I'd never heard of anything like it. And the warranty is like this. They provide cost-free maintenance for forever. Okay? So if we deliver your software that fails, it's our fault and we fix it for free. So if it has a lot of faults, we go out of business basically. Whereas when you buy anything from any software, if you look, no warranty, disclaimer, you do this at your own cost. Whatever happens, your fault. You're paying for the faults we give you to deal with. Okay, it's a different approach altogether, and they can afford to do that because they have confidence that the software they deliver is of that kind of quality. Of course, what happens in practice is, as the system runs for a while, you realize actually we wanted it to be slightly different, and that costs, of course. Is the difference between verification and validation, building it right and building the right thing. Okay, so the process of discharging this kind of proof obligation, where is it now again? The process of discharging this proof obligation is called natural deduction. And I wanted to go through with you the main concepts of natural deduction in the sequent calculus that is implemented in both the Spark tools and in Isabelle and in other proof tools available. C#, for instance, has something similar to this, and it's determined for this is called static analysis. It's when you do this kind of mechanical proof automatically. Usually it means you need to trade off between the kind of claims you can make and the kind of effort that you input. So no free lunch. But so the process is called natural deduction, and it's a system of inference rules whereby you construct arguments through a series of inferences, and you construct arguments about propositions for that. So you have some rules which are taken to be axioms, so things you take for granted, they are always true, and some other rules that you derive, they are proofs, so they are theorems or lemmas, auxiliary results of interest. The way to read a proof rule, I mean, somebody asked yesterday about where could you find this somewhere online. I found a tool called the Incredible Proof Machine that's worth having a look at. So remember me if I forget. Okay. But anyway, you get a premise is the set of hypotheses and conditions that you can assume to be true. A conclusion is what you want to prove, and the name of the rule is the name of the theorem or the name of the axiom that you're interested in. Side conditions have to do with certain rules whereby you can get so-called name capture. We're not going to get to that probably. It depends on how far we get. Most rules have no side conditions. So these rules of inference, when they are given and you take them for granted, they are so-called axioms. You don't want to have too many axioms because otherwise you end up with a contradictory situation whereby you can prove anything and then is useless. So having the smallest possible set of axioms is a good idea. The propositional rules follows the meaning of the truth tables, namely any proof with a truth table is a proof here and vice versa. They are equivalent to a certain extent. Okay? They differ in the sense that this scales, right? So if you have 10 variables, you can cope with 10 variables no problem. If you have 10 variables, you need 2 to the power of 10 entries in your table, and that is exponentially bad. I used Isabelle here to, I used the same encoding Isabelle, the theorem proof that I was showing you uses, but the using that book shows this is slightly different, but they have the same meaning, same principle. The way to read the proof trees is if you read the proof tree top down, you have two kinds of rules, introduction and elimination rules. I'll come back to this slide once I show you an example of a proof tree. Proofs work on well-formed formulae. So you do not want to have, you don't want to do proof on, say for instance, an expression that's not type correct or it hasn't been type checked or it doesn't pass. Okay, so you assume them to be well-formed formulae, namely you need to validate them first. It's a separate exercise. But once they have been validated, then if your propositions are valid, say, in the example you're talking here, I got the row present equals to nil, or row present equals to guard. So guard is a known type, is a known value, is a known name within your system. Then row present equals to nil becomes A as a proposition. I'm just talking about how this gets implemented. So if you then get all your atomic propositions that way as your set of well-formed formulae, then they remain well-formed if you use any of the logic connectives. Okay. The way that a program interprets this is by having an interpretation whereby for every atomic proposition in alpha, for every atomic proposition in alpha, you have a meaning for it. That's a Boolean. So you have either true or false for these. Think of this as your memory. That's exactly what the truth tables do. So think of the L there as the encoding of a truth table in a function. Certain notions that are important to understand. So if you get, when I showed this, where is it? Where is it? When I showed you this yesterday, when I said that all those were true, that meant it is a tautology. So the concepts then more formally are described as follows. There are three of them. So an interpretation satisfies the well-formed formulae if it yields true. So for example, this interpretation for A equals to true and B equals to true leads, it's a satisfiable interpretation for this particular proposition. Okay? So satisfiability has to do with finding what assignments to the variables of interest lead to true. Okay? Whereas validity or tautology is when you find interpretations that are always satisfiable, namely every single column, every single line there is true regardless of the interpretations you've given. So, for example, A or B, is this satisfiable, unsatisfiable, or a tautology? So if you take the interpretation for, like what we did yesterday for the, finding a counterexample, if you take an interpretation that makes, is there any interpretation that makes this true? So if A is true, then this is true. If B is true, then this is true. So this is clearly satisfiable. Okay. Is it a tautology? No, because if both are false, this is false. Okay. Similarly, how about this one? A and not A. Is this satisfiable? So, well, if this is true, if A is true, then you get true and something else, which is the something else. Then not true is false, so the result is false. Okay? It's not working, is it? No. Hello? You can hear me all right, can't you? Yeah, all right. Oh, now it is working. Right, okay, so I'll leave it then. Now, if A is false, false and something is just false. Therefore, whatever interpretation you give to A, the result is false. so it's unsatisfiable. So it's a contradiction. Okay? These concepts are important because you want to know, if you can find something to be unsatisfiable, you know you can stop working. It's like finding the counterexample, and that's what the tool's trying to do. Okay? The trouble is, in the proof search exercise, there are certain, say, for instance, that square root example, the tool just gave up. It couldn't know whether or not that particular final proof obligation was true or false. It couldn't find interpretations that would falsify it, and that's a counterexample for it to deal with, or would establish that it is true in general. It's a tautology. And at that point, it's up to you to then use other tools or use proof rules yourself to finish it off. Okay? So, how about this one? A or not A? Well, if A is true, true or something is true, so that's satisfiable. If A is false, false or something is the something. Not false is true, so the result is true. In other words, whatever interpretation you give to A, the result is true. Therefore, this is a tautology. Okay? Fine. So, what we're going to see now are the rules of the game, if you like, and then I'll go straight into many exercises. So, the rule of the game is, this business here about Isabelle is just for those who have interest into this. If they want to play with a tool, Isabelle is available in the labs. But what I really care about here are the proof rules only, because I'm not going to be using Isabelle to do these. But so, how do you do proof? Well, you apply the available proof rules by finding the right connective and then deciding whether you want to apply an introduction or an elimination rule. So, usually there are 2 or 3 rules per operator. So if you have negation, conjunction, disjunction, implication and equivalence, there are about 20-some rules. Okay? I give you the list of them, and in coursework exams I don't ask you to remember any of that. It's all there. Okay? The point is not remembering those rules, but understanding how to apply them. So the proof rule for conjunction is, if you know that A and B is true, then you are obliged to prove that they are both true separately. Okay? If you want to conclude that they are both true, then prove to me that they are true independently. Conversely, if you know they are both true, that's your premise, then you can deduce as a conclusion that either of them is true because you know that both together are true. Does that make sense? Just like truth tables, the truth table for conjunction says that they are true. So if they are true when they're both, so A and B is true when they're both true. Therefore, if I know that they are true, then I can deduce that either of them is true because that's what the truth table does. On the other hand, if I want to say whether or not this is true, I need to demonstrate that both A and B are true. Okay, let me try and, I don't know if that's going to be helpful or not, but so if you imagine, if you had something, what that's doing is this. So if I was to say if I'm claiming that this is true, then I better demonstrate that both A and B were true. That's what that law is saying. Is this the case? Is this true? And is this true? Okay? Whereas if I have, if I know, this is for that law there, A and B for A and B. Whereas if that's something that I know to be the case, if A and B being true is something that I do know, then I can deduce that A is true and that B is true. Okay? And that's what that one is saying there. Either if... Okay, so if on... Remember, what's underneath here, that's your conclusion. That's your premise, or what you can assume. So if you can assume they're both true, then you can deduce that either of them is true. If you need to show they're both true, you must find what the interpretation for them at the moment is. Okay, so here is a concrete example which I'll do a proof of with you. So the objective is to prove that conjunction commutes. So B and A is the same as A and B. Okay, so commutativity of conjunction. The proof tree for this is as follows. What's the main function symbol? It's n. That is the only one. Okay, so what rule can you apply? Conjunction introduction. If you're going upwards in the tree, you're doing introduction rules. That's what. Let me get back to this. So if you're going upwards in the tree, you're doing introduction rules. If you're going downwards in the tree, you're doing elimination rules. Okay. So, and these proof rules are by pattern matching. Okay. So if you think of it, it's like this. So the proof rule says I will match a. So I should have used another color here, but the proof rule is saying I will match something for A and something for B. The way that this would match is to say that the left-hand side. So let me use another name to avoid confusion. So if I had P and Q, I would get P and Q. So the left-hand side will become B, and that means I need to prove B there. The right-hand side is Q for A. That means I need to prove A. Oh, this is not. Yeah, the colors are now better. Okay. So when you get to a situation where you just have atomic propositions, then you're stuck. Basically, you only have a fact without anything else that you can do about it for now. But you still have your premise, and the premise says that I can assume that A and B is true. So if you apply elimination rules to that, you can deduce either A or B. Yeah? Which means it is what you want to, it is what your current goals are. So conjunction introduction, I got to that, and by, what's the one there? A and B, I got to A, and A and B, I got to B. Okay, and that was conjunction elimination 2 and conjunction elimination 1. Okay? Why? Because I've decided to, oh, this is a bit small. I'm still getting used to this thing. In here, you decide, okay, I don't care about A, and I want to show B. That's exactly what my proof obligation was. In here, I want to find out about A, so I forget about B. The 1 and 2 here has to do on which side do you delete. I'm not too fussed about the rule name, so long as the mechanics of the construction of the proof tree is correct. Okay? Although putting the rule names right is helpful. In Isabelle, that proof tree would be written with this little script here. I can show this to you if you're interested. But effectively, it's pretty much in a script or in a programming language, the description of what this thing done by hand was. Okay, you apply the conjunction introduction you apply a conj as an introduction rule and conj as an elimination rule twice, and it's called conjunct 1 and 2 in Isabelle. Right. Okay. So. You may assume that certain statements are temporarily true, like for example, if you have something like if A, then P else Q, okay? When you're dealing with P, you can assume that A is true. When you're dealing with Q, you can assume that A is false, okay? Temporarily. So after the then, the if condition is true, and after the else, the if condition is false, okay? You do that all the time when you're programming, don't you? So that's what that means. You have temporary, certain conditions can be temporarily true, just like in this example with the if then else. But it needs to be discharged somewhere else. In other words, you need to actually evaluate A to know which branch of the if then else you are going into. So the way this is described in a proof tree is by having assumption brackets or ceiling brackets to them and the context number where those assumptions were introduced. Okay. For disjunction, the rules is the first rule that have such situations. So disjunction has 2 introduction rules and 1 elimination rule. So you get, if you knew, again, it's close to how the truth tables work. If you knew that A or B is true, then you need to prove either one of them, because this conclusion is true if either A is true or B is true. So both branches of the tree would lead to a solution. Okay? On the other hand, if you want to show that, if you know that A or B is true, which one is the one that makes this valid? Well, it's either one or the other. So whatever condition you like, and this is something that confused most students, but again, exercises is what solves this. You basically say, if you want to prove something R, on the condition that A or B is true, you can assume A, you need to prove 2 things. You need to prove R assuming A, you need to prove B. Sorry, you need to prove R assuming A and proving R assuming B independently. So think again of this as the if then else situation where if B is not A, so A or not A, this is true. Okay, you're proving something there, and then you need to prove it for both when A is true and when A is false. A similar proof tree. Now for the disjunction elimination, I'll try and put this the other way around this time. So if we are proving that B or A is true, the first so the proof of interest is A or B is B or A. Okay, that's your premise. So if you reach this, you're finished, and that's your conclusion. So that's where you start. What can you do here? There is only one operator. So say if you apply disjunction introduction, you could apply disjunction introduction for making this B, for example, and that's disjunction introduction 1. Okay, those being the rules. And then what will I do next? Well, I only have a single atomic proposition. There are no other operators, therefore there is no other law available for me to apply. The other thing that I could do is to start from the top. So again, here you see, if you remember doing this kind of calculation in school, or I don't know, in undergraduate courses in discrete maths, you can, if you're doing any algebraic proof, you can start from either side of the equation and you simplify away, right? So sometimes it's easier to simplify one side than the other side, and you choose. That's the same thing going on here. Okay. Either you simplify your premises or you simplify your conclusion to get towards your goal, and that's the difference between backward and forward proof. Now, in this case, the only law applicable here, what's the functional symbol of interest is OR. So the only law applicable is disjunction elimination. Okay. How do you apply the law? Well, by pattern matching. So if the pattern matching is A or B being there, so I'll take A to be A, B to be B. All right, so I can assume A there, I can assume B there. What do I want my R to be? It's entirely up to you. This is disjunction elimination 1. Sorry, disjunction elimination, and that creates context 1. That's where those assumptions are introduced. So what's the R? Well, the only thing I have at the moment is B. Okay? So if I take my R to be B, then this fits here just nicely. So I have A or B. What the rule says, this is very mechanical, okay? It's syntactic and mechanical, so you need to pattern match and substitute. So I'm matching A for A, B for B, and B for R. Okay? Because that's what I've got to prove. Okay? So that means the law looks like this now. Is that too small? Or is it okay? So you need to prove A or B is your premise. So this bit of the tree is done. You need to prove B and you've got A. You need to prove B and you've got B. Oh well, this is finished. And I'm done there as well. This is disjunction elimination 1. But this part here is unprovable. It's a dead end. Because I can assume A and I need to prove B. They're completely different and there's nothing that I can do anymore. I'm stuck. Okay. Well, what do you do next? We've started this by pruning the tree going upwards by forgetting about A, and then it came back to bite us. If you do it the other way around and you were to prune B, you would get the same the other way around. Okay? The point of the exercise here being you cannot really, tree pruning or basically forgetting information is dangerous and it could lead to dead ends. That's why there isn't an algorithm that could decide what to do. You need a heuristic or a human, in this case a heuristic, but in some other proof situations scratching your head and thinking what to do next. So if both of these situations would fail, I'll try and write a bit bigger. So it's the wrong thing to do to the disjunction and introduction either side. Yeah? You see that? No? Okay, I'll do it again. If I had B, or I'll put this on both. If I had B or A, and I put a B there, an A or B here, I have this situation, and I am lost. I can't finish that proof. This proof is finished, this one is finished as well, and this one is stuck. Similarly, if I was to apply the same principle to the other side, this side is finished, and this side is stuck the other way around. This one is finished as well. Okay? If I was to complete this, what law was this one? Disjunction elimination 1. This was disjunction introduction 1. Disjunction elimination. This was disjunction introduction 2. And this was disjunction elimination. Both failed, and they both failed similarly because you end up, what you forgot, we decided to prune A here, and that's exactly what we needed. We had asked to help in the proof of B, which was what remained. Conversely, when we decided to forget B, that's exactly what we had when we needed to prove A. Okay? So this tells you something about the process here, namely the decision to forget or prune the tree was too early. Okay? The only thing you could do in this particular case, the other way around, is to will I be able to do that? Yeah. Okay. If those two laws failed, what else could you do? Well, trying this with a different R. So A or B, where I will assume A and I'll assume B. What can you choose for R? You can choose anything you like. I know that this sounds a bit strange to begin with, and trust me, it comes to you with exercise. Okay, it's like riding a bicycle. Okay, first time, if you remember, riding a bicycle is a very strange experience because you suddenly lose your balance and you need to kind of coordinate hand and feet and everything, and then eventually you get the hang of it, and then eventually you're good at it. Okay, if you do enough. If you don't, there's that much you can watch somebody else do it. You're not gonna get it by that way. Okay, so it's exercise, really. Okay, that's why I'm starting early, and I know that this beginning is a bit strange. Okay, so R here, if I've tried eliminating both sides, and that's all that I could do going up, then, well, I'll take B or A for R. So if I pattern match B or A for R, then I've got my conclusion for R. Okay, this is, if the law, remember, what's the law like? The law is, I'll use all the letters to avoid confusion again. I'm picking A to be P, B to be Q, and A or B, and B or A to be R. Okay, it's by pattern matching. So if it's by pattern matching, then I'm going to have A. Well, I can use it here, can I? I'm going to have A for P there. I'm going to have B for Q there. P becomes A. Q becomes B, and R becomes B or A. Okay? Now, what would you do next? What laws are available for disjunction introduction? Come on, there are only two. So if I now say disjunction introduction 1, namely, or 2, either way, so I want, now is the time, what happened here? I forgot about A and got a B, I forgot about B and got an A. Well, if I forgot about the B there, I'll get an A, and that's exactly what I have. If I do that the other way around here, is exactly what I have, and I'm finished on all sides. Okay? In other words, the lesson there is, if you have any kind of disjunction elimination, you must prove, you can't take advantage of the assumptions that are given, and that's the discharging process at play. If you're going to assume A or B, you need to reach a conclusion by either mean. Okay? You can't shortcut your proof. You need to demonstrate, well, if you assume A was true, you need to finish. If you assume that B was true, you need to finish. And that's the price to pay for having extra information added and available for you. And that's the business of discharged assumptions there. Okay? Oops. Implication works similarly. So disjunction elimination is the most, disjunction and negation operators are the most tricky ones I find from students' comments and experience. Okay, so that's the one that you probably need to work on most, but we'll see. We'll see more of those soon enough. Before the break, I want to show you the laws for the other two operators so that we spend most of the next lecture on exercises. Okay? So implication introduction. Implication has only two laws. Implication introduction, implication elimination, also known as modus ponens. And it says if you have that A implies B, then you're supposed to prove B assuming A. Okay. Think of the if-then-else case. If implication is a filter, what's the truth table for implication? When A is true, then you need to prove, then it's the result of B that matters. When A is false, you don't care. Okay? So, similarly here, well, all that you need to do is prove B really, assuming A, whatever its value is. Because if it is, if A is false, then you can use that later on, and I'll show this when we deal with negation, to prove that this is a theorem. Conversely, if you want to find out anything about B, namely, if you know that A implies B, you can get to B so long as A was true, because if A wasn't true, then B didn't matter. Implication or equivalence is relatively straightforward in the sense that A is equivalent to B if they imply each other. Okay. Think of if you think about this in set theory, it's like so a set S is equal to a set T if S is a subset of T and T is a subset of S. Okay, it's a similar notion. So equivalence is double implication. Conversely, if you know that two things are equivalent, then you can unpick which side of the equivalence you'd like to deal with. Okay? In algebra, it's similar. If x equals to I, then x is less than or equal to I, or y is less than or equal to x. Okay? I don't want to go into force just yet, force and negation elimination. I want to do more exercise before I come to this. So let's have a 5 minutes break, and then next we're going to do exercises, and I want to talk to you about the coursework, which is also here. Yeah, so 5 minutes. Oh, I haven't given this yet, so I'll be talking about it. Ah, right, I see. You mean that one?
Yes.
Oh, alright, okay.
Thank you very much. May I ask you one more question?
Sure.
In 53 lambda calculus, is
Alright.
it any...
It's similar to the lambda calc. You've seen that before. I gave this yesterday.
It wasn't like...
You don't have it.
It wasn't like that, but the concept was the same.
It is the same. You can, in fact, Isabel is an implementation of type lambda calculus. So you can encode all this in lambda calculus, basically. So you can say that, say for instance, lambda x of true is the same as, lambda x of x is the same as true. Lambda x of, I forgot now. The point is, there is a implementation of the lambda calculus of propositional logic, and that's what Isabel does. So if you know lambda calculus,
it wasn't only in theory. I mean, we had a concept, and we had to transform the English language to how to say, to equations of lambda calculus.
That's right. So in the lambda calculus, what happens is you will get beta substitutions and alpha substitutions to simplify a particular formula, and that's. Let me see if I find it here. I was actually reading about this recently because some guy. Come on. Oh, my computer is not. I'll find this and I'll show you.
Okay,
yeah?
okay. Thank you very much.
Where did you do your first degree?
In Herodvat.
In what?
Herodvat and Edinburgh.
Oh, Edinburgh. Ah, Edinburgh. Yeah. But in what? Inherit what?
Yeah.
Ah, right. All right. Okay. Do you know what's his name?
The lecturer.
Yeah. So
Yeah,
there was
whose book?
Gutman. I know that Gutman Grove and what's his name?
It was...
Forgot his name. Oh, he was head of department at one point.
if I remember well, my lecturer was Kuzbu.
Right. No, I don't know.
But
I don't know all the people there, but I know a few.
I think she's still there.
Right.
Yeah,
Yeah, I know her too. I've been there a few times and I've worked with people from it, so it's a
Okay.
nice place.
Yeah. Nice campus.
Yeah, it is a very nice campus. Lovely walks there.
Yeah, it's the lake too.
Yep.
It's fun.
Let me just see if I find the paper that I was talking about here. I'll show you.
Okay, thanks.
Sure.
find them on your own. You come to me if you need help. Yeah.
So where is he? So yeah, you see, there is complete logic in the lambda calculus. Anybody else want some of them? Huh? Oh, right, yeah, yeah. Sure. Good. So, I've just given you some exercise I want to do for the rest of today. So I'm just trying to find here something to put up. No. Right, so you all have an exercise sheet there, right? And exercise 2.1. So let me put that up. Maybe 2. Oh well, I can do that like this, can't I? Does that work? So 2.1 and 2.2 is about truth tables and doing defining whether or not something is a tautology, namely if all rows in the right hand side of a truth table construction are true. So I suggest you do 2.1 and 2.2 in your own time between now and the practical. And I wanted to spend some time to you today doing 2.4 because it's about proof trees and it's a bit more involved. Okay. If we have time, I can, I don't know, or in the practical, I can pick one of the exercises in 2.1 and 2.2 for doing together as well. Okay. But as I said, it is about practicing basically. Okay. So I'm assuming you are okay with truth tables because it's very basic and close to how programming works. Are you okay with that, or do you want me to do something on truth table as well as proof trees? No answer, I'll take whatever answer I want, which is go to doing proof trees. I'm happy to do truth tables if you need, or if you want to. No? Okay. So, proof trees it is. So, do them in your own time and come to me either by email or in the practical or, well, whenever. Next time we meet, which I think is on Thursday. Right. So, I want to do exercise 2.4a, okay? And on 2.4a, can you all there see that side? I mean, I have a choice there, right? So, everybody else has it? Yeah, sure. Okay, so if you look at the second page, so this is the coursework, okay? Namely, to write the proof tree for these three expressions, okay? You have it? No. Okay. Oh, then do you? Sorry. So the coursework is about doing these three proof trees, okay? Now, for now, I don't want to get there yet, okay? Because I want before to do 2.4a, all right? So at the back, you've got this table, okay? This table is all the laws you are allowed to use. Everything else you need to prove or build a proof tree yourself, okay? Right. So I won't put this one up here so that I can project them both, okay? But then I will assume you're going to be watching or looking at this table to suggest to me what to do. Okay? So the exercise I want to do is 2.4a. And 2.4a says P and Q or R if and only if P and Q or P and R. Okay? That's what I need to prove. That's my conclusion. Yeah? Is that too small? Should I zoom in? Or no, that should be alright. Okay? So that's my conclusion. So if that's my conclusion, I'll draw a line there. And with any proof, the first thing that you do is to think, okay, does this make sense? Do I believe this is true in general? As an exercise, you can draw the truth table for this and see. But this is like a distributivity law between conjunction and disjunction. Okay? If you take, in algebra, similarly, you would have, say, for instance, P plus Q times R is the same as P plus Q times P plus R. Okay? So it's a similar property, distributivity of conjunction over disjunction. And you're proving it. We're demonstrating that that is indeed true. What's the proof true for that? Okay. Do they distribute? So for example, I don't know, summation does not distribute over division, but distributes over multiplication, for instance. So is it true, is it the case that conjunction distributes over disjunction? Do you remember at the beginning when I was showing you one of the Spark files, it had a file that had a series of laws, a series of extra information about arithmetic. This is an example of extra information. Stuff that you accumulate, accrete knowledge about in terms of your function symbols or operators of interest in order to simplify your proofs. Okay? So think of this as a low-level proof, which obviously every theorem proof or tool will have. It is true, but we need to demonstrate it. Okay, so if you look at your tables there, the first thing that you do is to identify the main function symbol. What's the main function symbol in this? Based on the precedences and binding power of the various operators. How does this tree look like? If I also put parentheses everywhere, where would they be? Is it P and Q implies, sorry, Q or R if and only if that? No. The parentheses would be here, right? Okay? So the main symbol is this one. Yeah? So the main symbol is if and only if. Okay. What direction am I going? Up. I'm applying an introduction rule then. Okay? I'm going in this direction. So I'm applying my introduction rule. What's the main function symbol? If and only if. In the table, the only introduction rule for if and only if gives you two implications. Yeah? So quite mechanically, if you take the left-hand side, it's basically the left-hand side implies the right-hand side. Yeah? And the same the other way around. So I have two proofs to do here, which is P and Q or R implies P and Q or P and R, and then I have on the other side P and Q or P and R implies P and Q or R. And this was by if and only if introduction. Oops. Okay? So the parentheses obviously in this one are here and here and there. Okay? So I took in the table, I took A for being this side, and therefore I have A implies something, and then something implies A, and I took this side to be B, and that's exactly what's in there. Okay? So it's by pattern matching. It's very mechanical and very precise. Right? Okay. So what's the main function symbol now? I have two things to prove, two goals. Okay? You know you're finished when you get to either premises or assumptions or nothing on the top of the tree. Okay? So I haven't finished yet. And in this case, I can assume nothing. I was given nothing. Okay? I need to prove this in general, tautologically. So, what's the main function symbol? It's that one and that one. As you get practice, you can do this in tandem like I'm doing, but I will instead go slowly and do one side at a time. Okay? So, I'll do the left-hand side first. So the main function symbol is implication. The direction of travel is upwards. So I'm doing an introduction rule for implication. What's the law for introduction? Well, is that a choice? No, there's only one. Okay. So far, I've applied two laws, and they were the only ones that I could possibly apply. Therefore, it's no choice at all. You're just basically mechanically applying the rules of the game. Okay? And soon enough, or well, in the one with disjunction that I showed you, the last proof that I was showing you, there was choice, and choice led to different outcomes, and different outcomes led to error or solution. Okay? And this will happen here as well. We'll see soon enough. Okay? But so far, the choice is not there really. It's just a matter of picking the right law based on the main function symbol. Okay? So, if that's the main function symbol and you're applying implication introduction, that's going to be your B, that's going to be your A. So what goes on the top of the bar? P and Q, or P and R. And this is by implication introduction. And then I can assume A, which is P and Q or R. Okay? Huh? Oh, you can see. Sorry. Too high. All right. I will actually look in there. P and Q or R. Yeah? In the law, you see there is you should put numbers or some marker to tell you where this assumption came from. Okay? Because you don't want to have what do you call it? You don't want to have assumptions used in the wrong context. Let me give a concrete example of that. If I was to do this in here, implication introduction, again, it's P and Q or R, and I can assume P and Q or P and R. Well, if I could use that assumption over here, then I'm finished. And that's like, what the hell is going on? I'm cheating. It's too easy. And that's what it means. Namely, there is a barrier there in the sense that this assumption was introduced here. Therefore, it can only be used upwards from this tree and nowhere else. Okay? Whereas that assumption was introduced there, so therefore, that's why they cannot cross over. Okay? Is that clear? Okay. Right. So, what do I do next here? So, from the previous experience, when I pruned a disjunction too early, I got into trouble. Right? Where is it? On this one. When I pruned it early and I forgot about some information, it came to bite me whatever way I went. So the same will happen here if I try to prune this or that. You're going to see it. Or shall I try something else? And then what else? Oh, come on. What? So, okay, which side do you want to do first? Yeah? This one, left side. Okay. Oh, well, left. Your left, yeah. Okay, so what do I do next? What's the main function symbol? Same story as before. Or, okay? So you're going up. Therefore, you are doing, you can either apply disjunction introduction 1 or 2. So you can prune the tree this side or that side. Yeah? So choose one. Yeah, it's the first year in here without a blackboard. This would be funny because usually I wipe and I won't be able to wipe now, but there you go. The advantage though, you get this on recap and then at least you can look at it again. But yeah, which side do you want to prune? Come on. deduction, introduction, you're going to get what? If I choose the same, okay, I'll choose that side, all right? So I'll say P and Q, okay? And I've basically applied introduction 1. I pruned that side there, yeah? Same thing. What's the main function symbol here? Is end. So if I apply end introduction, so end introduction, I get P and Q to prove, okay? So all that I have done here was to mechanically apply on the main function symbol its key introduction rules, nothing else, okay? Blind. I'll just, yeah, fine, apply to the main function symbol to the end, okay? Now I've got to atomic propositions. I have nothing else that I can do with them, so the best that I can do is look at my assumptions. Looking at my assumptions, what could I do with that to reach P and with that to reach Q? They both contain P and Q, therefore it should be possible to unlock either P or Q to finish my proof, yeah? Okay, that's where trial and error starts, okay? So if we were to have, you could do P and Q or R. What laws could you apply going downwards? If you're going downwards, it's an elimination law, yeah? And if it's an elimination law, then for what's the main function symbol? It's end. So then you can have end elimination 1 or 2, and therefore you get to P. Oh, sorry about the color coding there. Or you get to Q or R. Okay? Both steps are valid. This would be this would be end elimination 1 and end elimination 2. Okay? I could do those 2 steps. This one, the left one, fits exactly one of my goals, which is P. So that sounds like a good idea for this one. Okay? This doesn't quite fit Q, but alright, it's promising. It does have Q in it. Okay? So if we follow that path, and why I did it on another piece of paper, it's because it's an exploration. I'm not committing to it yet. Okay? And you will see, in proof search, it's, as I said before, it's like navigating yourself in a city somewhere where you only have a compass and you know where east is and you're kind of trying to navigate around, okay? So it's a search, and sometimes you fail and you go back and you get to a dead alley and you need to go back, and then eventually you get to your destination, okay? Which is completing the tree. In this case then, I would say, okay, this side is fine. I have a P and Q or R, and this is conjunction elimination 1, assumption 1, or A, I don't know if you don't want to use numbers, use letters. Let's check this tree. I went all the way up using laws that I knew or was given, laws that are in here, and I got to the top of the tree. All that I have is an assumption that was discharged in the right context. So this A was introduced here, so I'm in the right, I can apply this assumption here, so I'm done on that subtree. Okay? You are done when you got to all subtrees being complete or closed. Okay? So now to the other side, is that clear up to here? Yeah? Okay, so on the other side you get Q, and we know by doing this I will get to Q or R, okay? What else could I do here? I'm going down, that's the main function symbol. So what else could I do on this particular term? This one I've already used and I'm all right. So what law does this fit? I'm going down, so which side of this am I in? Elimination, yeah? How many elimination laws are there for disjunction? 1. So there's only one thing that I can do. Pick that law, okay? So if I'm picking that law, then I'm taking A for Q, B for R, and therefore I can assume Q there, and I can assume R here. And who is my R that I'm matching it against? Well, I don't know, I haven't picked it yet. So I'll call it C to avoid confusion with letters. Okay? So in my exploration, I know that if I apply or elimination, that's the only thing that I can apply, right? The pattern matching will give me an assumption on Q, an assumption on R, and I can still pick whatever I want for C. Okay? And if I do that, then I am stuffed because there are no more function symbols, therefore just atomic propositions, and then I'm in a world with just atomic propositions. So I really can't do anything else but choose C wisely. Well, the choice there then becomes, if I choose C to be Q itself, okay, then I would have the following, right? I would have Q or R, P and Q or R, and then Q there, R here. Okay, that's just applying disjunction elimination. And in that case, Q will match this Q, but I have a situation whereby Q will match, so that's fine. I generate 3 subtrees. One leads to an assumption that's been discharged, and that's fine. Another leads to another assumption that has been discharged, that's fine. And then I have one whereby I have Q or R, and then I'm stuck. Okay, just as I said before, we were stuck. Where is the other one? Just as we were stuck with this one, namely, if you prune too early, that's what you end up with. Mismatch between your goals and your assumptions. Okay. So following this path fails, so I'll stop here. So this failed, and it failed over here. Why? Because I forgot an R, and it came back to haunt me. Yeah? So what we need to do is not prune the R just yet. If we follow the same strategy as before, what was the strategy before? Apply or elimination as late as possible. Okay? If you think about this strategically, what we've been up to, we've chosen introduction rules for function symbols where we had no choice. Yeah? So, if and only if, no choice, introduction rule for it. Implication, no choice, introduction rule for it. Disjunction, well, stop because you may prune the wrong end and you don't know which one it is. Okay? I'm basically talking you through heuristic search for proof. Okay? In this case, these heuristics are, apart from disjunction elimination, everything else is pretty, there are algorithms and heuristics that describe this, and that's why some of those proof obligations the Spark tools found were true automatically, because the tools managed to construct this tree for you. Okay, but when they fail, like in the one I showed, then you need to construct the tree yourself, and that's what that Isabelle proof was doing. Okay? And because at the bottom of the bottom line of any safety critical system is a proof of some kind, understanding how proof works at its basic is important. Okay? Right. So what do we do then? I won't redraw all this. I will start again from... I guess I can do it like this. I'll start again from here. Okay? So if that was the mistake, up to here I was fine, and when I pruned it, I got into trouble. So I won't prune it. And instead I will start again. What do I have? I had P and Q or R. Okay. Yeah? Oh, you can't see. Sorry. P and Q or R. Okay. I know from this exercise that I can get easily to P, but then, and from here that I can get to Q or R, and I can choose a C, whatever that C is. Yeah? So if I choose a C, whatever that C is, and I know I shouldn't prune this too early, then if I make that decision again, if I try again to think of okay, I have P and Q or R, I can go to Q or R for that, and then I can assume Q and assume R, and I need to choose something for C. What if I get this expression there to be my C? Okay? Do you follow? So if I do that, then what I end up with is what? There is my C underneath the bar. At the top of the bar, I'll get Q or R. And then I have to prove P and Q, and P and Q or P and R twice, P and Q or P and R, where in here I can assume Q and in there I can assume R. Yeah? And this is by OR elimination. Okay? I've just applied OR elimination. OR elimination on what? Well, that's my A, that's my B, and that's my C. So then I can assume A and prove the same C, and I can assume R and prove the same C, and these are completely separate. Right. I have now 3 new things to prove, so I went from a situation where I had 1 thing to prove to 3 things to prove. And you may think, well, hold on a moment, that's too bad and make my life more difficult. Well, on the one hand, that's true, but on the other hand, you have multiple function symbols here, and you're trying to demonstrate how they distribute. So, in a way, you are trying to unpick their distribution out in there. Okay, that's the intuition behind it. The P, you know what to do. The Q and R, that's the step that demonstrates that they distribute, and that's why you're proving them separately for Q and R. Okay? So you have 3 things to prove. The first one is your disjunction, or so-called cut rule, and that can come from the assumption generated earlier. We know that from a previous failure by end elimination, end elimination 2. Okay? I know that this assumption can be used because it was discharged here, so it's in this tree. Anywhere else above here, this can be used, so that's okay, that's done. Okay? Now, those are the 2 sides. What do I do with them? Come on, what's the main function symbol in this? Oh, disjunction, yeah? We know from the previous experience that when we prune too early, we got stuck in both ways, right? Now we are in a situation where we could prune it again. Then the question is, will it be too early? Well, if you look at it, if you prune this side, you have to demonstrate later on P and Q. Q you've got, P comes from this, and we knew that from the previous failure, right? Sorry, in this case here, we knew we can get to P easily, okay? The trouble was getting to Q. Well, we now have a new situation where we have the Q. So pruning now is okay. You've unlocked the Q. So I will apply or elimination, sorry, or introduction. I'm going upwards. That's the main function symbol. So I will apply or introduction 1 and get P and Q. And then I will apply what's the main function symbol, and I'm going upwards, so it's an introduction, no choice. P and Q separately. Q is proved already in this context there, so it's context B over there, so that's B and that's B. And P, we know, can be found through QLR. So at the top of my tree, I've got one assumption generated here, so it's the right context, this is done. The same assumption, so this is done. And another one, which was generated there, so anywhere above here is okay. So that's also done. Okay? And that means this side is, so this is done, this is done, this is done, this side is finished. The other side is pretty much the same, so you prune the other side, you prune P and Q because you know R, so you get P and R, and that gives you P and R. R you've got, and P you can get by the same means, P and Q or R and A. Okay? So, if we stop and think about this and start again from the bottom, we've applied introduction rules on the main function symbols without thinking much until we got to a disjunction. Oh, sorry, over here. Until we got to a disjunction. That if we pruned earlier would give us trouble. So we didn't prune it earlier because we understood what that trouble was, and we unpicked each side as our conditions of interest. We then have three things to prove. One that comes from the assumption generated by the implication. The other two are proved by doing the pruning on either side, getting to either Q or R, and then the Q and R comes from assumptions over here, and the P gets proved by the assumption over there. Okay? That's what I mean by your argument has evidence to demonstrate why you say this is right. It's not my opinion, it's not because I'm an expert on whatever, it's because you can just tell me what were your inference rules, what are your axioms, and then how your heuristic search work. And if you don't want to trust it, here are the rules, apply it yourself and you'll get to the same proof. Okay? So, what I was saying earlier about, what is it? Come on, computer. What happened? Why doesn't it go away? What I was saying earlier about these rules that the Spark tools use are pretty much like the table. Where is the table now? Pretty much like this table, where they pick the right rules and then apply them in an algorithm to describe the tree of interest, this, okay? And then for the tree that it can't complete algorithmically, it says, sorry, I give up, I couldn't do. So this one, it found a tree for it. It didn't show it to you, but if you don't trust it, you can ask, okay, how did you get to the tree? Please explain it. And it would give you the inference rules applied, namely, application, if and only introduction, application elimination, and so on. And you just chase them down and build the tree yourself. Or it will say, sorry, I can't do this one, so I'm not sure. Maybe it's a proof, maybe it isn't. It's up to you. Okay? In practice, say for instance, you get about, I don't know, hundreds to thousands of such proofs to do. Okay? In some contexts, you get, each proof has millions of inferences, so the tree is enormous. Okay? You have no chance of doing this by hand, but say and you see that yourselves when you start doing the Spark programs, that it throws at you a number of proof obligations, some of which it's discharged automatically. That's what's going on behind the scenes. The Spark tools are building these trees for you. Okay. And when it fails, the reason why it fails, it's similar to the reason we failed. It took a path that it wasn't quite the right one to take, and then it didn't know what to do. Okay. Right. We finished the left-hand side of this. We still have this side to do. Okay. For the sake of, so on this side, I will follow as I was before here. Okay. So, what's the main symbol? What's the main function symbol? So on this side, I've applied the same things. Equivalence introduction, implication introduction, and now I've got this. I have an end in there as the main symbol. So what do? End introduction, and then I get to P and Q or R. Yeah, and that's by end introduction. Okay. What could I do again? I could apply or elimination on or introduction on either side, and that would lead to the same problem as before. So when you apply disjunction introduction, you need to be very careful. And I'll talk about rules of thumb here. These slides actually has this at the end, certain heuristics. Right, so we have two goals to deal with, and we've got that as, they both talk about P, they both talk about Q and R, so we are in good shape. So I won't, for now, prune either side because we know this is not going to work, okay? Or if you want, do that on your own later and you'll see how it fails. But remember something else I mentioned earlier, failure is productive. We've learned now about pruning the tree too early leading to a particular kind of failure, namely you end up with propositions that don't quite match because what doesn't match is exactly what you forgot or chose to forget. Yeah. So if I'm going the other way around, downwards from this assumption, okay, so if I am there and I'm coming down, what's the main function symbol? It's OR. That means it's an elimination rule. Okay? And if it's an elimination rule, that means I have to choose my C underneath that. And what will the C be? Well, whatever that is, it means I'll be able to prove that C for P and Q and prove that same C for P and R. Okay? So we need to make a choice for that C. What do you want? I have two things here. Arguably, I shouldn't have done the end introduction yet, but in this case it will be okay either way. So if I choose the C to be P, okay? So if I choose the C to be P, I end up with, I'm running out of space in this, isn't I? So I will have P or Q, P and Q, or P and R. And I chose for my C to be P. That means I have P and Q, because it's this one, yeah? This one is my A. This one is my B. This one is my C. So I have my A there. I'll have my B here, P and R. That's my B. And my C will go there twice, okay? So, do you see that this is going to work? Because you can do conjunction elimination on the side that ignores Q and ignores R, and you get T of P. Okay, so all right, so that sounds like a plan for this one. So this was a good choice, and that means I will put here P. I'll put here a P and Q, or P and R. And then I get P and P, and I can choose P and Q, P and R. This was what I could have assumed in the first place, and these are separate. And then I'm done. Now, if we check it, I went from the initial goal all the way up, whereby at the top of my tree I have assumption 2, which was introduced here, so that's fine, it's the right context. Assumption 3, which was introduced there, should have put the number there. So this is OR elimination 3. This is end elimination 1 and end elimination 1. The top of my tree only contains assumptions that were discharged. These ones came from there, that one came from here, and this one has no assumptions. So at the top of my tree I have only discharged assumptions. So that is finished. I now have to do that one. Okay. This one is going to be pretty similar. If you take Q or R for your C, I'll do it here for the sake of space. So if you take Q or R for your C, you end up having this. You end up having Q or R, and then you have P and Q or P and R with 2, and then you have Q or R, and you're going to have P and Q, P and R, separate. Now then, because what you've got to prove talks about Q and R only, you can definitely prove P no problem. Yeah? So that means you can in this case because I have Q there, I will prune R here, so I get Q here, and then I get P and Q there. And I'm done. And in the other case I get R and P and R, and I'm done. Whereby this was OR elimination 4, that's number 4. This is OR introduction 1, OR introduction 2, and this is end elimination 2 and end elimination 2. Okay? And that completes, because this Q or R matches that. I won't match the 2 in there because now it became a bit messy. Yeah, I need to see how I'm going to do this. I've played with this on my own on these projectors, but not having a whiteboard is a bit strange for me. I'll get there. So maybe like this. Yeah. So the important point here is that we got at the top of the tree where we used only assumptions that were discharged at the right place. So this one came from there, and the other 2 came from the disjunction elimination. And at the top of the tree as a whole, every part of the tree now contains discharged assumptions. And that's when you know you're done. Okay? So in the end, we end up with multiple sub-goals of interest. Okay? Before we finish, I wanted to show you something that you may find useful. This was a project from a student in Edinburgh. No, not Edinburgh, Munich. It does use Isabelle on the bottom of it. It basically is a visualization of the stuff well, proof trees, okay? And it's driven by a engine that is pretty much like what you get in Isabelle, but written in Haskell instead. So, for instance, this one we proved earlier, the commutativity of end. Yeah, remember that? So if we want to see it, let me clear it. So here is what it looks different, okay? But it's the same principle. You've got introduction rules and elimination rules. So this is saying, think of what's on the right-hand side as being what's in the bottom of the tree, and on the left-hand side what's on the top. Or I don't know, this particular funny icons. But you are saying that there is an introduction rule for conjunction, and there is an elimination rule for conjunction where you can choose either side. Okay? It gives you a hint to say you've got two blocks at the moment, your premise and your conclusion, number one and number two, but you, with four, you should finish. So it kind of gives you a hint of how many laws should you apply. Namely, it's telling you how to navigate this landscape to say, well, if you've done more than four, you can still get to a proof, no problem, but four is kind of your optimum. Okay? If you ever, there's a game in the App Store called Dragon Ball, or Dragon Z, Dragon whatever. It teaches children algebra. It's lovely because it starts with pictures and various symbols. You end up with pretty much primary school, secondary school algebra. This does that for proof trees in the sense that it gives you a sense of how to build them in a game almost. Okay. So in this case, what did we apply? We applied introduction for end, and that's that. And then we applied elimination rule. In here they optimize this. Ooh. Oh, I failed there. What? What have I done wrong? Hold on. Oh no, that one. I'm still not quite good at this. So this was my elimination rule, this was my introduction rule. I now need to put them to match. That's my B. That's my A. When it succeeds, it tells you. So it has a very rigid way of connecting the rules, but at least it's a way of checking. It's a way of doing visual proof rather than using the theorem prover. If we were to use Isabelle for it, I'm not going to show this in Isabelle, but it's incredible.pm. Well, let's see if I find another task so that we finish on that. Do they have? Oh yeah, that's the one, isn't it? Yeah. So these two are pretty much ours. Yeah. The one we are doing just now, distributivity. These are the two sides of this proof. So this one here is that side. Is that right? Oh, it's the other way around. It's the other operator. It's the distributivity of conjunction over disjunction rather than the other way around. But it's pretty much the same proof tree. The same principles behind the proof tree. You get 10 blocks. So you're going to apply 10 rules, which is not too dissimilar to how many we've applied here. We've applied, if you're doing just this branch, you applied 1, 2, 3, 4. And for the Q side, where is it now? 5, 6, 7, 8, 9, 10. Okay. So I don't know, somebody said to me that they found this easier, or they could play around with it and it gave them some confidence. Okay. It is slightly different in the sense that in the elimination rules you've seen that I didn't apply the elimination rule twice. I applied the same elimination rule and then pulled them droplets into the right connector. Okay. But it's a visualization at least that helps you understand what's going on. Okay. And yeah, it's quite, you can create your own as well. So the coursework is those three exercises. So basically it's building those three proof trees, okay? We will not, you probably, by all means try, but I think some of them you might be able to, others you will not, because it depends on some other laws we haven't seen yet, the rest of the table for false and negation, okay? What I'm going to do from now on, so on Thursday and Friday, is talk you through the laws that are missing, namely the negation laws and the false law, and proving the excluded middle one, because this is like a theorem, a lemma, not really an axiom. And then doing some more exercise. I do suggest you try doing, say, 2-4 in the Using Z books exercise. This exercise, by the way, comes from the Using Z book. Okay? And the Using Z book, let me show you something here that will be useful as well. If you go to the Using Z book, you get an electronic version of the book, and in it, if you go to chapter 2, you get truth tables, proof trees, the description of all this stuff in quite great detail, okay? Various exercises, some example proof trees. The exercises come from the book, and they have suggestions there. And as I said, it explains various proof trees. This stuff becomes easier as you exercise them and fail a few times, like riding a bike. Okay? If you don't do that, the coursework will be a dreadful thing to go through, at least my part, and you're going to get terribly stressed because the deadline is on the 8th, which is a couple of weeks from now. So I strongly suggest start now. Okay? Because with all goodwill in the world, closer to the time when you're all stressed about it and 10 of you come at once, that will be that mean I'll be able to answer immediately, okay? So please start early, okay? Please start early, it's for your own benefit. As I said, if that's the only time in your life you're going to see any of this, great, at least understand where it fits in the bigger scheme of things, okay? Namely, if you want to create a high assurance argument, that's what you do, and that's why testing, that you demonstrate the absence of error